Yeah. So, welcome back, everybody. Now the second talk is by Matias Delgadino. He's from University of Texas at Austin, and he will be talking about interacting diffusions and propagation.
Thank you for the introduction, and thank you for the opportunity to share something. I guess it's my first talk since the pandemic started, so yeah, it's welcome back. Okay, so I'll be talking about hopefully a problem that you guys have seen at some point. So we have particles xi n, which are indistinguishable. Okay, and they're going to just all satisfy some SD, which is xi dot is equal to -1/m, the sum over J of the gradient of some interacting potential xi xj with some let's call it some temperature Pi dot. Okay, and for simplicity, I'm going to assume that all of these particles are sampled from some initial distribution, which is rho initial, which is something. Okay. Yeah. So here, I mean, usually people, or I mean, a lot of things like people look at interactions that are xi minus xj. These are a bit more general. The proofs are basically the same. Okay. So I guess the idea of sampling all at the same time is basically saying that all particles are chaotic. Okay. So the idea of propagation of chaos is if you have some chaotic initial distribution, then they will stay chaotic for all later times. Okay, so just to give the setup, I mean, here we're going to have xi, which is in omega, which can be the torus or some convex set in Rd. And I'm not going to discuss much of the boundary conditions, but the appropriate boundary conditions. Okay. So the main assumption that I'm going to do in terms of regularity of all of this is that the Hessian of W is bounded below by some constant times the identity. Okay, so this is what it's usually called lambda convex, but I'm going to use lambda for the log Sobolev inequality, so let's call this K, and this is something that is dependent on. Okay, so what is the problem that we're trying to understand here is we're trying to understand what is the statistical behavior of this system of particles as the number of particles go to infinity, and we want to try to recover some description that is much simpler than understanding the system. Okay, so it's similar to, I guess, what Carsten was talking to us last time, but this is in a much simpler model in which this Pi is just the running. So, yeah, so as n to infinity, we want to just recover the statistical behavior. So the perspective I'm going to look at here is the Liouville's equation. So we want to take n to infinity and actually get some mean field behavior of this. So the perspective is the Liouville's equation, or forward Kolmogorov, depends how you want to call it. And so what I'm going to be tracking is the log of x1 through xn, which is a symmetric, so it's just notation. This is going to be equal to rho n, which is a symmetric probability measure in omega to the n. Okay, so the state space becomes larger and larger, but the advantage of looking at the whole law of all the particles at the same time is that it satisfies a linear equation. Okay, so in this case, if you allow yourself to look at a lot of dimensions, then what happens is that you end up getting an equation which is linear and looks like this. Okay, I'm gonna keep track of the temperature because that's gonna be important at some point. But for now, it's just adding some extra thing. Okay, so if I try to find the law of these particles, just because I have an Brownian motion associated to each particle, then I'm going to have this Fokker-Planck equation in which the potential Hn is just given as the sum over I and j, 1 over 2n of W xi. So yeah, I mean, the remark is this is a linear equation, but the problem is that as n goes to infinity, the state space grows because this is set up in probabilities of omega t. Okay. So the classical theorem here is the theorem which is due to Schnitzman. I'm not sure if it was even before him, which basically says that if gradient of W is Lipschitz, then the two Wasserstein distance between the kth marginal of rho n and the mean field tensorized k is less or equal than e to the c t minus 1 divided by square root of n. Okay, so the kth, this is the kth marginal. Okay, and these are k copies of the mean field description. And one of the things I'm going to always do is, if I want this constant, all of the constant appearing here to be independent of dimension, I need to normalize of what is the dimension that I'm looking at. And so here, if I want to normalize dimension, I need to take 1 over square root of k. Okay, and from now on, I'm just going to denote this by the two Wasserstein distance with a little overline over it. And so wherever I put an overline over anything means that it's independent of dimension, and it's something that you take the limit of dimension to infinity, you actually get something that's not. Okay. All right, so, and just to make sure that we're all on the same page, rho m mean field is the unique solution to dt rho mf minus the divergence of the gradient W rho mf equals to temperature times the Laplacian. Rho mf with initial condition, same initial condition. Okay. Any questions about like this result? This kind of the setup, like start, try to improve on this. So is the setup clear on this? Yep. Sure. So okay, so one couple of remarks at the beginning. First, here we're assuming that this gradient of W is Lipschitz. This can be, of course, reduced a bit, and I mean there is quite a lot of work, especially recently, on more singular kernels. Okay, and so this would be Javelin 1, then rest, also Javelin 1. And then if you are looking at maybe specifically the Coulomb case, there's quite a bit of work of FKT, and then I won't actually try to explain. Yeah, okay. Oh, there's a bit of a delay, I guess.
Yes, there's a bit of a delay.
Okay, hopefully I'll catch up. If not,
you need to touch your computer, I think.
plug in.
You need to maybe actually do with your computer. Is there one that doesn't? So,
No, I think it's
No?
the exact values might have gotten disconnected, which is not great. But okay. Well, so there you go. Perfect. Okay, we'll leave this around just in case. Okay. All right. So this all of the idea is that these are for more similar kernels, and like you can get similar type of estimates, but now you're doing it for values that is much more irregular. Oh. Okay. So yeah, this is not going to be fun. Yeah. All right, so I guess the question that I'm going to try to answer, or at least like tackle a bit, is this exponential growing in time necessary? Okay, so I mean, it's a fairly natural question, like we have an estimate, but when can we expect that we have a uniform in time propagation of chaos and when we cannot? Okay, so if we answer that question, so is e to the ct necessary? And of course, if I'm asking the question, then probably have the answer. And like the idea is that not always. Okay, and the first result of this direction was by Malraux, which was able to do it for W convex. Okay, and actually uniformly. So if W is uniformly convex, you can actually get an estimate, which I'll just write again, D2 of rho and k, rho and f tensor k is less or equal than some constant that is independent of k now, of 1 times e to the minus mt divided by square root. Okay, something that becomes square root of n in the large time, but it's 0 at the beginning. Okay, so this was like in the case of non-convexity, but the question is, can we push this further, and what is the limit of this thing? Okay, so when do we cannot expect this anymore? And so then there was some work by Eberle that did some new coupling techniques, and he was able to show that in the large noise or small interactions, you get the same result. Okay. In fact, he doesn't work in the D2 distance, but he works in the D1 distance. Okay, because he's able to do some specific computations using something that is similar to the D1 distance to be able to get this. Okay. Yeah. So okay, the question is, what is the natural obstruction? And the answer, natural obstruction and the idea or the answer that I want to claim is that this is phase transitions. Okay, so phase transitions is a fancy word for saying that something is changing in your system as you change some control parameter. Okay, so as we change the temperature, all of a sudden something that seems simple became a bit more complicated. Okay, and I mean it's like water going to ice in like sort of physical terms, but in more general systems, this can actually also happen. Let me try to think. Remember the mouses. Search screen. Should have better this. So can you see something here? Trying to get this. When you try to use too much technology at the same time, it's balance. Okay, maybe you've seen this video before. For the first time, real experiment shows that some take place 22 Okay, so what's the idea here is that, I mean, you have a system in which the particles were just like spatially homogeneous, like going on a torus. And then if you put enough pressure on them, then eventually you will see a phase transition. And so instead of looking at some like uniform steady state, they will start clustering. Okay, and so the idea is that for high enough temperature or low enough pressure, you only expect this to be. I will do this again. You expect the system to be well behaved, but when the temperature starts becoming lower, then sorry about this. I would have practiced this better before. When the temperature lowers, then you can start expecting that there is cluster states, and then there is actually something weird happening. Okay, so in more mathematical terms, is that there is a non-uniqueness of steady states. Okay, and this is a non-uniqueness of steady states at the mean field level. Okay, so going back to the Liouville equation, the Liouville equation was given by a linear equation, while the mean field equation is nonlinear. Okay, so what's the main point here that I want to make is that this equation here always has a unique steady state. And this one doesn't necessarily have a unique steady state. Okay, and so phase transitions are happening when this equation stops having a unique steady state. Okay, so the idea is for large enough temperature, the mean field equation has a unique steady state. But as we start lowering the temperature, the nonlinearity can kick in, and you can actually start seeing more than one solution to the state equation. Okay, and so what you were saying was instead of temperature was pressure, but the idea is the same. Okay, so what happens in this case? So what is the unique steady state of this guy? The unique steady state is given by the Gibbs measure, which is mn e to the minus t inverse hn divided by zn. Okay, and this is the unique steady state. So in particular, what we can say is that rho n up to some compactness, which I don't care much about, is that rho n converges to mn as the time goes to infinity. Okay, this is a unique steady state that you can have. But rho mf will converge to a possibly different steady state. Okay, so all right. So what's kind of the conjecture that we can say is that we have uniform in time propagation of chaos. If and only if the mean field equation has a unique non-degenerate steady state. Okay. So I'm not going to be able to prove this, but this would be kind of the role in what I would like to kind of say, and this is that for some analysis, yeah, at some point, I mean, if we have like a unique non-degenerate steady state, then we can actually say that we have uniform propagation of chaos and the other way. Okay, so it's kind of, I just show that, I mean, in a sense, if you know that you have the mean field equation has more than one steady state, and you already know that you cannot have uniform time. Yes. Okay, so that would be the idea. So the way that we're going to non-degenerate means that the linearized operator around the steady state is has a spectral. Okay. So the quantifying. So the way that we're going to try to tackle this is quantifying convergence to equilibrium. Okay. And the way that we're going to do this is by looking at the log Sobolev inequality. And the nice thing about the log Sobolev inequality is that is, in a sense, dimension independent. So this is the right kind of guy to actually look for in the limit when n goes to infinity. Okay, so I'm going to define the relative entropy. So the relative entropy between rho n and mn is just going to be the integral, the log of the quotient, integrated against rho n. And of course, when I said that I want to normalize everything, I'm just going to take a factor of 1. Okay, and the nice thing about this is that the relative entropy in this sense actually converges to something nice. Okay, and so the point of how does the log Sobolev inequality comes in is that if I take the time derivative of the relative entropy, what I get is the Fisher information, which is the gradient of the log of rho n divided by mn squared integrated against rho n. Okay, and this is the definition, definition of the relative entropy. So this would be minus the relative entropy, and here I have a 1 over m of rho n. Okay, and so what is the log Sobolev inequality? So the log Sobolev inequality is to obtain exponential decay of the relative entropy. So in particular, I can say that this is less or equal than lambda n LSI of the relative entropy itself. Okay, so if I have these inequalities minus, then I have exponential convergence in relative entropy of rho n to m as time goes to infinity. And just lambda n LSI is going to be equal to the infimum over rho n of the relative Fisher information divided by the relative entropy. Okay. Okay, so in a sense, like if I'm asking, if I have these kind of problems with the what's happening as time goes to infinity, the question is, when does this guy degenerate? So when do we actually know that the limit when n goes to infinity, this actually goes to 0 or not? Okay, and in fact, the question is, what is the limit of this? Okay, so one thing is that for each finite n, this is always positive. I mean, if I'm in the torus, it's always positive, as long as it has some smoothness. So this is positive, but it's not necessarily uniformly positive. Okay, and so then kind of the idea is to quantify when it goes to 0. Okay, so the kind of view that I started looking at this started with Jose and Greg Pavliotis a long time ago. That we started looking at how we could actually pass to the limit in the gradient flow structure of the Liouville equation to the gradient flow structure in the mean field limit. Okay, so if what I'm going to say is just sort of gradient flow kind of formalism, is that rho n is the gradient flow of this relative entropy under the D2 distance on symmetric probability measures to the end. Okay? And the mean field is the grad flow of mean field energy, which is just equal to the entropy plus the interaction energy. Okay, so with the two on the probabilities of omega. Okay, so the point is that, I mean, we saw the structure, we wanted to say something about it. So at least the nicest thing was to try to recover the same result just by passing to the limit from one structure to the other. And the idea was to use one of Sarah's sort of results in terms of passing to the limit in the evolutionary variation inequality, so which is called like Moscow convergence. So if you have convex energies, then the limit of the gradient flow converges to the limit. Okay, so this is usually referred to as Moscow convergence. Okay, and what you need to actually identify is what is the limit of these metrics and what is the limit of the space. Okay, so the state space is getting larger and larger, but still we can actually recognize what is the limit of this. So this is a classical result in probability, which is called fluid savage or the kinetic, depends on which country you're from. And the symmetric probability matrix is probabilities in omega to the n converge as n goes to infinity to the probabilities of the probabilities form. So what does this say? So this say that any limit of the symmetric probabilities in omega n can be written, okay, I'll get there. Can be written as a convex combination of chaotic measures. Okay, and the topology for this is cylindrical functions, which is the same topology as in propagation of chaos results, which is just the continuous functions of the probabilities of omega. Okay, and that doesn't necessarily have to make sense, but the idea is that you can actually identify what the limiting space is, and you can even actually show what the limit is when n goes to infinity of the Bassel time distance, which happens to be the Bassel time distance, the two Bassel time distance on the metric space P of omega E2. Okay, so yeah, just this, there is a 1 over n sort of in front of the Bassel time 2 distance. The idea is that if you're doing a symmetric probability measures, you can actually identify what the limit is, and this is the 2 Bassel time distance, but now on a metric space. Okay, and this was done by a Korean machine. Okay, and then okay, so we identify the limit of the space, we identify the limit of the metric, so we have to identify the limit of the functional, and the idea is that the relative entropy functional gamma converges to some potential function, but this is a weird one. So this E infinity of some Q, let's say, is equal to the integral over the probabilities of omega of the mean field energy evaluated at rho integrated against this measure. Okay, where Q is an element. Q is an element in the probabilities of the probabilities form. Okay, and again, this result we didn't do. This result was already known by the people in statistical physics, and this was done by Messer and Spohn like 20-30 years ago. Okay, so the point is that we were able to identify all of the limits of this. So then we can actually recover Schnitzmann's results just by saying, okay, the gradient flow at the level of symmetric probability measures in omega n converges to the gradient flow of this energy, which actually coincides with the description we were doing. Okay, so hopefully that wasn't too abstract, but okay. What this gives you is the idea of you can actually pass to the limit in quantities like E bar. And so then when you're trying to take the when you're trying to take the limit as n goes to infinity of the log Sobolev inequality, you can actually pass to the limit in this way. And recover something in terms of the mean field. Okay, so that's kind of the main point. So we can actually pass to the limit in that thing. I mean, it's not that easy, but at least that's the idea. So another result, which is we can actually also say, is that the relative Fisher information gamma converges to the integral over the probabilities of omega of the dissipation of rho d q. Okay, so where the dissipation comes out of the computation of taking the mean field energy evaluated at the mean field flow is equal to minus the dissipation. It's getting worse. Okay, I don't really have much time for this. Let's see. Okay, now I'm gonna share like slides that are here. Cool. Great. Oh, this is not fun.
It's coming.
It's coming.
Patience.
Patience is a virtue, I guess. So, okay, the relative Fisher information is converging to the integral over the dissipation of the integral over the dissipation on this measure. Again, it's a potential, but now it's a potential at the infinite dimension. Okay, yeah, I'm not going to prove this, it's way too complicated, but yeah, the idea is that morally what we're saying is that the limit when n goes to infinity of lambda n LSI is going to be equal to the mean field. The mean field, which is the infimum over the measures of the dissipation of rho over the mean field energy of. Okay, so the log Sobolev inequality is converging to the dissipation in the mean field. Okay, so the idea, if we were able to prove this, okay, and I can only prove one inequality in this, but the other one should also be true. If we are able to prove this, then the idea is as long as the mean field log Sobolev inequality, the mean field dissipation inequality is positive, then the limit of lambda n of LSI does not degenerate. Okay, so that's, I mean, the idea is pretty simple. The idea is pretty simple. What I showed almost kind of shows it, but yeah, there is a linearization that we're missing in infinite dimensions that we don't know about. Okay, so the theorem kind of says, yeah, lim sup when n goes to infinity of lambda n LSI is less or equal than lambda n. And the other thing is that if the mean field has a non-minimizing critical point, then the lambda n LSI is going to be less or equal than C divided by n. Okay, so in some sense, this is quantifying the metastability of the steady states of the mean field equation. Okay, so if you have steady states of the mean field equation, these are going to be metastable in the particle dynamics, and this is kind of giving you the time step. I'm not sure this is sharp, but should be close. Okay, yeah, and then the other, okay, so then once we kind of figured out this and we were not able to prove the equality, even though it looks pretty reasonable as long as you have that the linearization at the steady state is non-trivial. Yeah, so what else do I want to say here? So the idea would be the other way, now the other way around. So assume that the limit of lambda n LSI is positive, then we have uniform time propagation case. Okay, so connecting a bit with what I had said before, if we have a unique steady state that is non-degenerate, then we should have uniform time propagation of chaos. The idea is that we have a unique steady state that is non-degenerate, then this thing will be positive, strictly positive. Okay, so the idea would be, so if we can say that the limit is strictly positive, then we expect that this guy is strictly positive, and we actually can have uniform time. Okay, and the proof of this is like interpolating between the classical Smith-Solomon result and then the limiting sort of thing for the Gibbs measure and the limiting time. So I only have 5 minutes, no? So I don't.
10 minutes.
10 minutes.
9.
10 minutes max. Cool. Okay, so maybe I guess I'll listen to that. So what we need to use here is that the distance, again, the V2 distance between Mn and rho infinity tensor n is less or equal than C over square root of n. Okay, so we can actually say that the limiting state for the particle dynamics is actually close to the limiting state for the mean field dynamics. Okay, and we actually need to show this. I mean, I looked fairly hard in the literature and I could never find a result like this. But then at the end, it was particularly simple how to do it. And the idea was to use that the LSI implies the Talleyrand inequality. Okay, so the LSI is saying that so lambda times E is less or equal than I bar, and this guy implies that lambda times the V2 distance squared divided by 2 is less or equal than the relative. Okay, and so this seems like really abstract and seems like quite complicated to prove, but in fact this inequality is actually quite easy to show, even if you think in one dimension and you actually just translate what everything does. And in fact, like the whole paper is kind of done with this type of idea. So you define this guy to be f. The efficient information is f prime squared. Okay, so what I'm saying is lambda times f is less or equal than f prime squared. This, okay, and so here I'm assuming that f of 0 is equal to 0, f is positive. Then what you actually obtain is that lambda times x squared divided by 2 is less or equal than f of x. Okay, so and if you actually think in the gradient flow sense, this is what you're doing. Okay, so if you consider one sort of in time, in a sense, what's happening, you can actually show this thing, and you can do it over the curve of the gradient flow. Okay, and yeah, so if you combine the log Sobolev and the Talleyrand inequality, you obtain this. Okay, and the idea of how to do this. So if you take, yeah, so V2 Mn rho infinity tensor n, this is going to be less or equal than 2 over lambda V2 squared rho infinity tensor n Mn, which is less or equal than 2 over lambda squared, the relative entropy, which is less or equal, did I get, sorry, I wrote the same thing again. This should be a relative entropy, and this should be a relative efficient information. And this is just less or equal than a constant divided by what? Squared Normalize. Should be it. Okay, and yeah, not sure if I did a great job, but the point of saying is that once we have this inequality, we can combine this with the original inequality for from Schnitzman, and then actually get a uniform time result. Okay, because we know that the particle dynamics are going exponentially fast to Mn. We know that the mean field dynamics are going exponentially fast to rho infinity, and then they're closed in the middle. So if you interpolate between the two things, you obtain a uniform in time estimate that depends a bit on how this is going to. How big this is. Okay. Let me see. I don't really have much time, but okay, yeah. What this result allows you to do is to actually look at the fluctuations at the level of the stationary state, which time. Okay. Yeah, I guess that was an interesting thing to say, but what I'm saying here is like, so what we're looking at is 1 over n, the sum over xi from I equals to 1 up to n. The is converging to expectation of x. Okay, so this is the result that we're looking at. But I mean, what we can start looking at is what happens when we take square root of n, 1 over n, the sum of I equals to 1 to n of delta xi minus the expectation of x, and then here you get normal with some variance sigma. Okay, so the idea is that you can actually do this at this level when you start looking at the fluctuations, where eta n is just the square root of n of the sum of delta xi minus rho infinity. Okay, and this is the right scaling, and the idea is that now we have tightness of this problem because we have the previous estimate. Okay, so the idea is when n goes to infinity, you can actually show that eta n converges to eta infinity, which is the unique solution in some appropriate sense of the linearized operator at rho infinity, eta infinity, plus the divergence of rho infinity with space-time weights. Okay, so why does this start becoming interesting in terms of phase transitions? Is that this actually tells you that the fluctuations are going to become infinity at a phase transition. Okay, so at a phase transition, this guy is going to degenerate, and so then what you actually expect is that the fluctuations at equilibrium are going to become deterministic, and they're going to be concentrated around the eigenvector of the generation of this. So in fact, I mean, I don't know, I feel I've heard a lot of times that, you know, the climate change, how do you know that climate change is happening? It's not because the temperatures are rising, it's just because we have more and more fluctuations around like of our weather. So the idea is that at least if you look at the fluctuations, you should be in the continuous case, you should actually be able to understand in which sense is your system having a phase transition. Okay, so the idea is that at the phase transition, the D2 distance between rho n infinity tensor n and mn actually behave like 1 over n to a quarter, and then if you scale appropriately, you actually should obtain something deterministic. Okay, so the fluctuations do explode at the phase transition, and then you should expect that eta n converges to something deterministic, which is the eigenvector of okay, so morally, if you're looking at the fluctuations, you should be able to see when things are going to start breaking down, and the way that you can actually see if they're going to break down is by looking at the fluctuations. This was something that there is some literature about, but like few actual results. Okay, anyways, I think I'll stop here. So I'm not too late. Thank you for your attention.
Yeah. Any questions?
So, in case in which you don't have a unique answer, is there some gradient flow tool that can help you, for example, to see if it is stable condition, like something non-global when you don't have a unique minimum, but somehow.
But towards which type of results?
Like to see how these multiple critical points, if we start close one of them.
Yeah, and the thing is that, I mean, as n goes to infinity, if you start at one of them,
Okay.
you will stay.
You
at
will
one.
stay.
Yeah,
Yeah.
yeah. But I mean, but the time scale is the time scale that comes out of the beginning of the talk. I mean, you have this grows e to the ct. And so then, I mean, that's kind of the time scale that you actually find in these things. So you will.
So in this case, it's kind of optimal.
I haven't shown that. I'm not sure about that, but I would guess. Yes.
So on the limiting object, you can see the phase transition, and it's known when it happens, at which temperature.
No, I mean, no. Like, in fact, that's like, it's kind of solving a nonlinear problem when it will happen. You can, in some really simple models, identify when, like, that there will be a phase transition or not. But in general, like, and I didn't say this, I'm sorry to prepare better, is like large temperature, no phase transition. Small interactions, no phase transition. Now, finding exactly when there is a phase transition can only be done in explicit modes.
And people don't know how it depends on the potential. Like, if convexity is really something that is intrinsic to the problem, for example, or not.
So in general, I mean, the simplest case is sort of, let's say that we take the spatially homogeneous case. So your energy becomes rho log rho plus W convolution rho. Okay. And so now there is the concept of HWD. This is convex linearly. Okay. And the idea is that you can actually write this as the integral of W hat times rho hat squared. Okay, and this guy is convex as long as this is positive.
But this is not now on the level of the.
This is the mean field.
But what happens on the infinite dimensional?
Same thing. This is potential energy.
It's exactly the same expression.
It's because this, like, you have to think of this as a potential of rho. So if the potential has more than one minimizer, then at the level of the infinite dimensionals, things stay linear. So if you have some correlations at the beginning, the same correlations will.
So, sorry, another question. So,
yeah.
Independently, let's say, on how this interaction potential. So if you put like a temperature sufficiently high on the other curve, you have some.
So if W is, let's say, Lipschitz, then yeah, we used like 2-scale log Sobolev to show that then you cannot have a phase transition, and in fact, this limit when lambda n when n goes to infinity of the LSI is actually positive.
If you restrict your class of interactions to pair potentials which are just depending on the distance, then you get some kind of symmetry that you could kind of, I don't know, if you have a torus that you could shift. How much would it be easier or more difficult? Is that somewhere kind of uniqueness? And I was thinking, would this be? Would you still have uniqueness also?
So I mean, you can have. I mean, I think Jose might be a better like to answer this question, but I think you can have like, yeah, it will help you because in a sense, like if you take away the like spatial homogeneity of it, then you expect that it's more likely you will have a unique sort of minimizing system. Versus if you look at the whole system, and like the classical XY model has that system, has that type of way, but I've never tried to do it, and I'm not sure if once you take out this spatial symmetry, Like if you take out the symmetry, then you still have the like thing that I'm talking about. I'm not 100% sure. Yeah.